Good day everybody, this is Charlie of MALABO and today's video is all about domestic wastewater treatment. But before anything else, we should first know what is domestic wastewater and why does it need to be treated. Wastewater derived from human activities in households such as bath, laundry, dishwashing, garbage disposal, toilets, etc. is called as domestic wastewater, which usually contains relatively small amounts of contaminants, but even small amount of pollutants can make a big impact on environment. Hence, a properly installed and maintained residual sewage treatment system for treating and disposing of household wastewater will minimize the impact on groundwater and surface water. Domestic wastewater treatment plays an important role in nowadays. Domestic waste treatment ensures that all household sewage is properly treated to make it safe, clean, and suitable for releasing back into the environment, lakes, and streams. Home sewage systems are designed to treat all of the liquid waste generated from residents. Possible contaminants in household wastewater include disease-causing bacteria, infectious viruses, household chemicals, and excess nutrients such as nitrate. Wastewater has historically been considered as a nuisance to be discarded in the cheapest, least offensive manner possible. This meant the use of or site disposal systems such as the pit privy and direct discharge into our lakes and streams. Over the last century, it has been recognized that this approach produces an undesirable impact on the environment. This led to a variety of treatment techniques that characterize the municipal treatment systems today that are the focal point of this chapter. So there are characteristics of wastewater. First is the physical characteristics of domestic wastewater. Wastewater temperatures normally range between 10 and 20 degrees Celsius. In general, the temperature of the wastewater will be higher than that of the water supply. This is because of the addition of warm water from households and heating within the plumbing system of the structure. The second one is the chemical characteristics of domestic wastewater. Because the number of chemical compounds found in wastewater is almost limitless, we normally restrict our consideration to a few general classes of compounds. These classes often are better known by the name of the test used to measure them than by what is included in the class. The biochemical oxygen demand, or the BOD5 test, which we discussed in the past video, is a case in point. Another closely related test is the chemical oxygen demand, or the COD test. Characteristics of industrial water. Industrial processes generate a wide variety of wastewater pollutants. The characteristics and levels of pollutants vary significantly from industry to industry. The Environmental Protection Agency, or the EPA, has grouped the pollutants into three categories: conventional pollutants, non-conventional pollutants, and priority pollutants. So the wastewater treatment standards under that one is the retreatment of industrial waste. Industrial wastewaters can pose serious hazards to municipal systems because the collection and treatment systems have not been designed to carry or treat them. The waste can damage sewers and interfere with the operation of treatment plants. They may pass through the wastewater treatment plant untreated, or they may concentrate in the sludge, rendering it a hazardous waste. Next is the municipal wastewater treatment system. The alternatives for municipal wastewater treatment fall into three major categories: the primary treatment, secondary treatment, and the tertiary treatment. It is commonly assumed that each of the degrees of treatment includes the previous steps. For example, primary treatment is assumed to include the pretreatment processes, which are the bar rack, grit chamber, and equalization basin. Likewise, the secondary treatment is assumed to include all the processes of primary treatment, like the mentioned earlier, the bar rack, grit chamber, equalization basin, and primary settling tank. So the purpose of pre-treatment is to provide protection to the wastewater treatment plant equipment that follows. In some older municipal plants, the equalization step may not be included. So the unit operations of pre-treatment. Several devices and structures are placed upstream of the primary treatment operation to provide protection to the wastewater treatment plant equipment. These devices and structures are classified as pre-treatment because they have little effect in reducing the BOD5. In industrial wastewater treatment plants where only soluble compounds are present, bar racks and grit chambers may be absent. Equalization is frequently required in industrial wastewater treatment plants. The first one is the bar racks. Typically, the first device encountered by the wastewater entering the plant is a bar rack. The primary purpose of the rack is to remove large objects that would damage or foul pumps, valves, and other mechanical equipment. Rags, logs, and other objects that find their way into the sewer are removed from the wastewater on the racks. In modern wastewater treatment plants, the racks are cleaned mechanically. The solid material is stored in a hopper and removed to a sanitary landfill at regular intervals. The second one is the grit chambers. Inert dense material such as sand, broken glass, silt, and pebbles is called a grit. If these materials are not removed from the wastewater, they abrade pumps and other mechanical devices, causing undue wear. In addition, they have a tendency to settle in corners and bends, reducing flow capacity and ultimately clogging pipes and channels. So there are two basic types of grit removal devices. First one is the aerated grit chambers. The spiral roll of the aerated grit chamber liquid drives the grit into a hopper which is located under the air diffuser assembly. The shearing action of the air bubbles is supposed to strip the inert grit of much of the organic material that adheres to its surface. The second one is the vortex grit chambers. Wastewater is brought into the chamber tangentially. At the center of the chamber, a rotating turbine with adjustable pitch blades along with a cone-shaped floor produces a spiraling donut-shaped flow pattern. This pattern tends to lift the lighter organic particles and settle the grit into a grit sump. The next one is the comminutors and macerators. Devices that are used to macerate wastewater solids such as rags, paper, plastic, and other materials by revolving Cutting bars are called comminutors. Comminutors are most commonly used in small wastewater treatment plants with flows less than zero point 0.2. These devices are placed downstream of the grit chambers to protect the cutting bars from abrasion. They are used as a replacement for the downstream bar rack, but must be installed with a hand-cleaned rack in parallel in case they fail. Comminutors may create a string of material such as rags that collect or downstream equipment. Because of this and the high maintenance cost, newer installations use a screen or a macerator. Second is the equalization. Flow equalization is not a treatment process in itself, but a technique that can be used to improve the effectiveness of both secondary and the tertiary wastewater treatment processes. Wastewater does not flow into a municipal wastewater treatment plant at a constant rate. The flow rate varies from hour to hour, reflecting the living habits of the area served. Primary treatment. So with the screening completed and the grit removed, the wastewater still contains light organic suspended solids, some of which can be removed from the sewage by gravity in a sedimentation tank. These tanks can be round or rectangular. The mass of settled solids is called raw sludge. The sludge is removed from the sedimentation tank by mechanical scrapers and pumps. Floating materials such as grease and oil rise to the surface of the sedimentation tank, where they are collected by a surface skimming system and removed from the tank for further processing. Primary sedimentation basins or primary tanks are characterized by type 2 flocculant settling. The Stokes equation cannot be used because the flocculating particles are continually changing in size, shape, and when water is entrapped in the floc specific gravity, there is no adequate mathematical relationship that can be used to describe type 2 settling. Laboratory tests with settling columns are used to develop design data. So the unit process of secondary treatment. So the wastewater microbiology, under that is the role of microorganisms. The stabilization of organic matter is accomplished biologically using a variety of microorganisms. The microorganisms convert the colloidal and dissolved carbonaceous organic matter into various gases and into protoplasm. Because protoplasm has a specific gravity slightly greater than that of water, it can be removed from the treated liquid by gravity settling. Another is the classification of microorganisms by kingdoms. Microorganisms are organized into 5 broad groups based on their structure and functional differences. The groups are called kingdoms. The 5 kingdoms are the animals, plants, protista, fungi, and bacteria. Classification for energy and carbon source. The relationship between the source of carbon and the source of energy for the microorganism is important. Carbon is the basic building block for cell synthesis. A source of energy must be obtained from outside the cell to enable synthesis to proceed. Our goal in wastewater treatment is to convert both the carbon and the energy into wastewater into the cells of microorganisms, which we can remove from the water by settling. Therefore, we wish to encourage the growth of organisms that use organic material for both their carbon and energy source. Classification by their relationship to oxygen. Bacteria also are classified by their ability or inability to utilize oxygen as a terminal electron acceptor in oxidation or reduction reactions. Obligate aerobes are microorganisms that must have oxygen as the terminal electron acceptor. When the wastewater contains oxygen and can support obligate aerobes, it is called aerobic. Classification by their preferred temperature regime. Each species of bacteria reproduces best within a limited range of temperatures. Four temperature ranges are used to classify bacteria. Those that grow best at temperature below 20 degrees Celsius are called psychophiles. Mesophiles grow best at temperatures between 25 degrees Celsius and 40 degrees Celsius. Between 45 and 60 degrees Celsius, the thermophiles grow best. Above 60 degrees Celsius, stenothermophiles grow best. Next is the bacterial biochemistry. Under that is the decomposition of waste. The type of electron acceptor available for catabolism determines the type of decomposition, that is aerobic, anoxic, or anaerobic, used by a mixed culture of microorganisms. Each type of decomposition has peculiar characteristics that affect its use in waste treatment. Next is the aerobic decomposition. In natural water bodies, the oxygen is measured as DO, or the dissolved oxygen. When oxygen is present, it is the only terminal electron acceptor used. Hence, the chemical end products of decomposition are primarily carbon dioxide, water, and new cell material. Odoriferous gaseous and end products are kept to a minimum. In healthy natural water systems, aerobic decomposition is the principal means of self-purification. Anoxic decomposition. Some microorganisms can use nitrate as the terminal electron acceptor in the absence of molecular oxygen. Oxidation by this route is called denitrification. Anaerobic decomposition. In order to achieve anaerobic decomposition, molecular oxygen and nitrate must not be present as terminal electron acceptors. Sulfate, carbon dioxide, and organic compounds that can be reduced serve as terminal electron acceptors. The reduction of sulfate results in the production of hydrogen sulfide and a group of equally odoriferous organic sulfur compounds called mercaptans. The anaerobic decomposition, or the fermentation of organic matter generally, is considered to be a three-step process. In the first step, waste components are hydrolyzed. In the second step, complex organic compounds are fermented to low molecular weight fatty acids or volatile acids. In the third step, or the last step, the organic acids are converted to methane. Carbon dioxide serves as the electron acceptor. Population dynamics. In the discussion of the behavior of bacterial cultures that follows, there is the inherent assumption that all the requirements for growth are initially present. Because these requirements are fairly extensive and stringent, it is worth taking a moment to recapitulate them. Activated sludge. The activated sludge process is a biological wastewater treatment technique in which a mixture of wastewater and biological sludge, or the microorganisms, is agitated and aerated. Because the microorganisms are suspended in the liquid wastewater, this process is known as a suspended growth process. The biological solids are subsequently separated from the treated wastewater and returned to the aeration process as needed. Completely mixed activated sludge process. The design formulas for the completely mixed activated sludge process are a mass balance application of the equations used to describe the kinetics of microbial growth. A mass balance diagram for the completely mixed system is already been tackled. The mass balance equations are written for the system boundary shown by the dashed line. Two mass balances are required to define the design of the reactor, one for the biomass and one for food. Plug flow with recycle. A plug flow reactor is one in which the fluid particles pass through the tank in sequence. Although it is difficult to achieve true plug flow, many long, narrow aeration tanks may be better approximated by plug flow than by completely mixed models. A kinetic model of a plug flow system is difficult to develop from basic mass balance equations. With two simplifying assumptions, Lawrence and McCarthy have developed a useful equation. Sludge return. Among the major decisions in developing a suspended growth reactor design is the selection of the mixed liquor volatile suspended solids, or the MLVSS, concentration and the corresponding mixed liquor suspended solids, or the MLSS concentration. The selection is not simple. It depends on the objective of the reactor, settling characteristics of the sludge, and the rate of recycle of sludge, called the sludge return rate or sludge return or return activated sludge. Sludge volume index, or the SVI, is determined from a standard laboratory test. The procedure involves measuring the MLSS and sludge settleability. A 1 liter sample of mixed liquor is obtained from the aeration tank as the discharge end. The sludge settleability is measured by filling a standard 1 liter graduated cylinder to the 1 liter mark, allowing undisturbed settling for 30 minutes, and then reading the volume occupied by the settled sludge. The MLSS is determined by filtering, drying, and weighing a second portion of the mixed liquor. Sludge production. The activated sludge process removes substrate, which exerts an oxygen demand by converting the food into new cell material and degrading the cell material while generating energy. This cell material ultimately becomes sludge that must be disposed of. Despite their problems in doing so, researchers have attempted to develop enough basic information on sludge production to permit a reliable design basis. Oxygen demand. Oxygen is used in those reactions required to degrade the substrate to produce the high-energy compounds required for cell synthesis and for respiration. For long SRT systems, the oxygen need for cell maintenance can be of the same order of magnitude as substrate metabolism. Process design considerations. The SRT selected for design is a function of the degree of treatment required. A high SRT or older sludge age result in a higher quantity of solids being carried in the system and a higher degree of treatment being obtained. A long SRT results in the production of less waste sludge. SRT values for designs of carbonaceous BOD5 removal are a function of the minimum temperature at which the reactor basin will be operated. Sludge problems. A bulking sludge is one of that has poor settling characteristics and poor compactability. There are two principal types of sludge bulking. The first is caused by the growth of filamentous organisms, and the second is caused by water trapped in the bacterial floc, thus reducing the density of the agglomerate and resulting in poor settling. Next one is the trickling filters. The trickling filter itself consists of a bed of coarse material such as stones, slats, or plastic materials over which wastewater is applied. Because the microorganisms that biodegrade the waste form a film on the media, this process is known as an attached growth process. Trickling filters have been a popular biological treatment process. The most widely used design for many years was simply a bed of stones from 1 to 3 meters deep through which the wastewater passed. Oxidation ponds. Treatment ponds have been used to treat wastewater for many years, particularly as wastewater treatment systems for small communities. Many terms have been used to describe the different types of systems employed in wastewater treatment. For example, in recent years, oxidation pond has been widely used as a collective term for all types of ponds. Originally, an oxidation pond was a pond that received partially treated wastewater, whereas a pond that received raw wastewater was known as a sewage lagoon. So types of ponds is the aerobic ponds. The aerobic pond is a shallow pond in which light penetrates to the bottom, thereby maintaining active algal photosynthesis throughout the entire system. During the daylight hours, large amounts of oxygen are supplied by the photosynthesis process. During the hours of darkness, um, wind mixing of the shallow water mass generally provides a high degree of surface aeration. Another one is the anaerobic pond. The magnitude of the organic loading and the availability of dissolved oxygen determine whether the biological activity in a treatment pond will occur under aerobic or anaerobic conditions. A pond may be maintained in an anaerobic condition by applying a BOD5 load that exceeds oxygen production from photosynthesis. And photosynthesis can be reduced by decreasing the surface area and increasing the depth. Anaerobic ponds become turbid from the presence of reduced metal sulfides. This restricts light penetration to the point that algal growth becomes negligible. The last one is the facultative pond. Of the 5 general classes of lagoons and ponds, facultative ponds are by far the most common type selected as wastewater treatment systems for small communities. Approximately 25% of the municipal wastewater treatment plants in the U.S. are ponds, and about 90% of these ponds are located in communities. Facultative ponds are popular for such treatment situations because long retention times facilitate the management of large fluctuations in wastewater flow and strength with no significant effect on effluent quality. The next one is the rotating biological contactors, or the RBC. The RBC process consists of a series of closely spaced discs. It's 3 to 5 meters in diameter, mounted on a horizontal shaft and rotated, while about one half of their surface area is immersed in wastewater, and the discs are typically constructed of lightweight plastic, and the speed of rotation of the disc is adjustable. Integrated fixed film activated sludge. This category includes any activated sludge system that incorporates a fixed film media in a suspended growth reactor. The purpose of fixed film media is to increase the biomass in the reactor. This offers the potential to reduce the basin size or to increase the capacity of an existing base in a retrofit application. Moving bed biofilm reactor. This process uses small plastic elements to support the growth of biofilm in the reactor. The suspended growth portion of the hybrid is designed as a complex mixed reactor. It is commonly mixed with aeration but may also be mixed with a mechanical mixer. But the process that I use returns sludge flow. Disinfection. It is the last treatment step in a secondary plant and is the addition of a disinfectant to the treated wastewater. The addition of chlorine gas or some other form of chlorine is the process most commonly used for wastewater disinfection in the United States. Chlorine is injected into the wastewater by automated feeding systems. Wastewater then flows into a basin where it is held for about 15 minutes to allow the chlorine into reaction with the pathogens. Tertiary wastewater treatment. Filtration. Secondary treatment processes such as the activated sludge process are highly efficient for removal of biodegradable colloidal and soluble organics. However, the typical effluent contains as much a higher BOD5 than one would expect from theory. The typical BOD is approximately 20 to 50 milligrams per liter. This is principally because the secondary clarifiers are not perfectly efficient at settling out the microorganisms from the biological treatment processes, and these organisms contribute both to the suspended solids and to the BOD5 because the process of biological decay of dead cells exert an oxygen demand. So there are types of filtration. First is the granular filtration and the membrane filtration, which has been discussed on the previous video. Carbon adsorption. The most practical available method for removing refractory organics is by adsorbing them on activated carbon. Adsorption is the accumulation of materials at an interface. The interface, in the case of wastewater and activated carbon, is the liquid or the solid boundary layer. Organic materials accumulate at the interface because of physical binding of the molecules to the solid surface. Carbon is activated by heating in the absence of oxygen. The activated process results in the formation of many pores within each carbon particle. Chemical phosphorus removal. All the polyphosphates or the molecularly dehydrated phosphates gradually hydrolyze in aqueous solution and revert to the orthoform from which they were derived. Phosphorus is typically found as monohydrogen phosphate in wastewater. The removal of phosphorus by chemical precipitation is typically accomplished by using one of three compounds. Biological phosphorus removal. In the biological phosphorus removal, or the BPR, or enhanced biological phosphorus removal, or the EBPR, as is it sometimes called, the phosphorus in the wastewater is incorporated into cell mass in excess of levels needed for cell synthesis and maintenance. The phosphorus contained in the biomass is removed from the process as biological sludge. Nitrogen control. Nitrogen in any soluble form is a nutrient and may need to be removed from wastewater to help control algal growth in the receiving body. In addition, nitrogen is the form of ammonia exerts as oxygen demand and can be toxic to fish. Removal of nitrogen can be accomplished either biologically or chemically. The biological processes are called nitrification or denitrification, or sometimes biological nitrogen removal, and the chemical process is called ammonia stripping. So the nitrification or denitrification is the natural nitrification process can be forced to occur in the activated sludge system by maintaining a cell detention time of 15 days in moderate climates and over 20 days in cold climates. While the ammonia stripping, the nitrogen in the form of ammonia can be removed chemically from water by raising the pH to convert ammonium ion into ammonia, which can then be stripped from the water by passing large quantities of air through the water. The process has no effect on nitrate, so the activated sludge process can be operated in a short cell detention time to prevent nitrification. Land treatment for sustainability. An alternative to the previously discussed tertiary treatment processes for producing an extremely high-quality effluent is offered by an approach called land treatment. Land treatment is the application of effluents, usually following secondary treatment on the land by one of the several available conventional irrigation methods. This approach uses wastewater and often the nutrients it contains as a resort rather than considering it as a disposal problem. Treatment is provided by natural processes as the effluent moves through the natural filter provided by soil and plants. Slow rate. Irrigation, the predominant land application method in use today, involves the application of effluent to the land for treatment and for meeting the growth needs of plants. The applied effluent is treated by physical, chemical, and biological means as it seeps into the soil. Effluent can be applied to crops or vegetation including forest land, either by sprinkling or by surface techniques, for purposes such as first, avoidance of the surface discharge of nutrients, economic return from use of water and nutrients to produce marketable crops, water conservation by exchange when lawns, parks, or golf courses are irrigated, and prevention and enlargement of green belts and open space. Overflow land. Overflow land flow is essentially a biological treatment process in which wastewater is applied over the upper reaches of sloped terraces and allowed to flow across the vegetated surface to run off collection ditches. The renovation is accomplished by physical, chemical, and biological means as the wastewater flows in a thin sheet down the relatively impervious slope. The next is the rapid infiltration. Rapid infiltration in infiltration percolation systems. Effluent is applied to the soil at higher rates by spreading in basins or by sprinkling. Treatment occurs as the water passes through the soil matrix. And the system objectives can include groundwater recharge, natural treatment followed by pumped withdrawal or the use of underdrains for recovery, and natural treatment where renovated water moves vertically and laterally in the soil and recharges a surface water course. So the sludge treatment. So there are basic processes for sludge treatment, and these are the following. First is the thickening. Thickening is the separating as much water as possible by gravity or flotation. Next is the stabilization, converting the organic solids to more refractory or inert forms so that they can be handled or used as soil conditioners without causing a nuisance or health hazard. These biochemical oxidation processes are called digestion. Third one is the conditioning, treating the sludge with chemicals or heat so that the water can be readily separated. Fourth is the dewatering, separating water by subjecting the sludge to vacuum, pressure, or drying. And the fifth one is the reduction, converting the solids to a stable form by wet oxidation or incineration. And these are chemical oxidation processes. They decrease the volume of sludge, hence the term reduction. So sources and characteristics of various sludges. Under that is the grit. Grit, the sand, broken glass, nuts, bolts, and other dense materials that is collected in the grit chamber is not true sludge in the sense that it is not fluid. However, it still requires disposal because grit can be drained of water easily and is relatively stable in terms of biological activity, and it is not biodegradable. It is generally trucked directly to a landfill without further treatment. Primary or raw sludge. Sludge from the bottom of the primary clarifiers contain from 3 to 8% solids. The solid fraction is approximately 70% organic matter, and this sludge rapidly becomes an anaerobic and is highly odoriferous. Secondary sludge. This sludge consists of microorganisms and inert materials that have been wasted from the secondary treatment processes. Thus, the solids are about 90% organic matter. When the supply of air is removed, This sludge also becomes anaerobic, creating noxious conditions if not treated before disposal. Solid's content depends on the source. The tertiary sludges. The characteristics of sludges from the tertiary treatment processes depend on the nature of the process. For example, phosphorus removal results in a chemical sludge that is difficult to handle and treat. When phosphorus removal occurs in the activated sludge process, the chemical sludge is combined with the biological sludge, making the latter more difficult to treat. Nitrogen removal by denitrification results in a biological sludge with properties very similar to those of waste activated sludge. Solids computation. Under that is the volume mass relationships. Because most wastewater treatment plants sludges are primarily water, the volume of the sludge is primarily a function of the water content. Thus, if we know the percent solids and the specific gravity of the solids, we can estimate the volume of the sludge. The solid matter in wastewater sludge is composed of fixed solids or the mineral and the volatile solids or the organic ones. Thickening. Thickening is usually accomplished in one of two ways. The solids are floated to the top of the liquid or the flotation, or are allowed to settle to the bottom or the gravity thickening. The goal is to remove as much water as possible before final dewatering or digestion of the sludge. The processes involved offer a low-cost means of reducing sludge volumes by a factor of 2 or more. The costs of thickening are usually more than offset by the resulting savings in the size and cost of downstream sludge processing equipment. So the flotation. In the flotation thickening processes, air is injected into the sludge under pressure. Under this pressure, a large amount of air can be dissolved in the sludge. The sludge then flows into the open tank where at atmospheric pressure, much of the air comes out of the solution as minute bubbles. The bubbles attach themselves to sludge solids particles and float them to the surface. The sludge forms a layer at the top of the tank. This layer is removed by a skimming mechanism for further processing. The process typically increases the solid's content of activated sludge from 0.51% to 3 to 6%. Flotation is especially effective on activated sludge, which is difficult to thicken by gravity. Gravity thickening is a simple and inexpensive process that has been used widely on primary sludges for many years. It is essentially a sedimentation process similar to that which occurs in all settling tanks. Sludge flows into a tank that is very similar in appearance to the circular clarifiers used in primary and secondary sedimentation. The solids are allowed to settle to the bottom where a heavy-duty mechanism scrapes them to a hopper from which they are withdrawn for further processing. Stabilization. The principal purposes of sludge stabilization are to break down the organic solids biochemically so that they are more stable or less odorous and less putrescible and more dewaterable, and to reduce the mass of sludge. If the sludge is too dewatered and burned, stabilization is not used. There are two basic stabilization processes in use. One is carried out in closed tanks devoid of oxygen and is called anaerobic digestion. The other approach injects air into the sludges to accomplish aerobic digestion. Aerobic digestion of biological sludges is nothing more than a continuation of the activated sludge process. When a culture of aerobic heterotrophs is placed in an environment containing a source of organic material, the microorganisms remove and utilize most of this material. A fraction of the organic material removed will be used for the synthesis of new biomass. The remaining material will be channeled into energy metabolism, and oxidize to carbon dioxide, water, and soluble inert materials to provide energy for both synthesis and maintenance functions. While the anaerobic digestion treatment of complex wastes involves three distinct stages. In the first stage, um, complex waste components, including fats, proteins, and polysaccharides, are hydrolyzed to their component subunits. This is accomplished by a heterogeneous group of facultative and anaerobic bacteria. These bacteria then subject the products of hydrolysis to fermentation and other metabolic processes, leading to the formation of simple organic compounds and hydrogen in a process called acidogenesis or acetogenesis. Sludge conditioning. Under that is the chemical conditioning. Several methods of conditioning sludge to facilitate the separation of the liquid and solids are available. One of the most commonly used is the addition of coagulants such as ferric chloride, lime, or organic polymers. Ash from incinerated sludge has also found use as a conditioning agent. As happens when coagulants are added to turbid water, chemical coagulants act to clump the solids together so that they are more easily separated from the water. Another is the heat treatment. Another conditioning approach is to heat sludge at high temperatures and pressures. Under these conditions, much like those of a pressure cooker, water that is bound up the solids is released, improving the dewatering characteristics of the sludge. Heat treatment has the advantage of producing a sludge that dewaters better than chemically conditioned sludge. Sludge dewatering. Under that is the sludge drying beds. The most popular method of sludge dewatering in the past has been the use of sludge drying beds. These beds are especially popular in small plants because of their simplicity of operation and maintenance. 77% of all U.S. wastewater treatment plants utilized drying beds. One half of all the municipal sludge produced in the U.S. was dewatered by this method. The next is the continuous belt filter presses, or the CBFP. The CBFP equipment used in treating wastewater sludges is the same as that used for water treatment plant sludges. It is successful in many normal mixed sludges. Typical dewatering results for digested mixed sludges with initial feed solids of 5% give a dewatered cake of 19% solids at a rate of 32.8 kilograms per hour squared meter. Reduction. Under that is the incineration. If sludge used as a soil conditioner is not practical, or if a site is not available for landfill using dewatered sludge, cities may turn to the alternative of sludge reduction. Incineration completely evaporates the moisture in the sludge and combusts the organic solids to a sterile ash. To minimize the amount of fuel used, the sludge must be dewatered as completely as possible before incineration. The exhaust gas from an incinerator must be treated carefully to avoid air pollution. Alternative sludge disposal techniques. So, landfilling. When there is an acceptable, convenient site, the landfill is typically selected for ultimate disposal of biosolids, grit, screenings, and other solids. Landfilling of biosolids and or ash in a sanitary landfill with municipal solid waste is regulated by the U.S. EPA under 40 CFR 258. Dewatering is typically required and stabilization may be required before the landfill can be used. If methane recovery is practiced and at the landfill site, the addition of biosolids may be welcome as it will increase gas production. Dedicated land disposal. Dedicated land disposal means the application of heavy sludge loadings to some finite land area and that has limited public access and has been set aside or dedicated for all time to the disposal of wastewater sludge. Dedicated land disposal does not mean end-place utilization. No crops may be grown. Dedicated sites typically receive liquid sludges. While application of the water sludges is possible, it is not common. In addition, disposal of the watered sludge in landfills is generally more cost-effective. Utilization. Wastewater solids may sometimes be used beneficially in waste other than as a soil nutrient. Of the several methods worthy of note, composting and co-firing with municipal solid waste are two that have receiving increasing amounts of interest in the last few years. Land application of biosolids. One of the methods of disposal of biosolids or wastewater sludge is by land application. Land application is defined as the spreading of biosolids on or just below the soil surface. The application to land for agricultural purposes is beneficial because the organic matter improves soil structure, soil aggregation, water holding capacity, water infiltration, and soil aeration. In addition, macronutrients such as the nitrogen, phosphorus, and potassium, and the micronutrients such as iron, manganese, copper, and zinc aid plant growth. These contributions also serve as a partial replacement for chemical fertilizers. Under that is the site selection. A critical step in land application of biosolids is the identification of a suitable site. Among the factors that must be considered are topography for the erosion potential, soil characteristics, depth of the groundwater, accessibility, proximity to critical areas such as domestic water supply, property boundaries, public access, and howl distance. The employment of a soil scientist to assist in the assessment is critical. Design loading rates. Nitrogen and heavy metals concentrations in the sludge are two of the major concerns in determining the sludge loading rate. The nitrogen limit is typically determined on an annual basis. Heavy metal loadings are based on long-term averages. The nitrogen loading rate is typically set to match the available nitrogen provided by commercial fertilizers. Application methods. Nitrogen. The application methods are broadly classified as liquid application and dewatered biosolids application. Liquid biosolids application is attractive because of its simplicity. Dewatering processes are not required. Solids concentrations range from 1 to 10%. The application method may be by vehicular application or by irrigation. So that would be all about the domestic wastewater treatment. And as a summary, household sewage treatment plant breaks down domestic waste via three major stages, which was discussed a while ago: the primary stage, the secondary stage, and the tertiary stage. In the primary stage, this is the first stage of sewage or wastewater treatment that removes about 40 to 60% of the suspended solids. It involves screening to remove large objects such as sticks, stones, etc., which can cause damage to tank inlets. It employs grit chamber, which slows down the flow of wastewater to allow grit to fall out naturally to the bottom of the tank where it can be removed. Primary clarifier or settling or sedimentation tank in this stage removes sinking and floating contaminants. And the partially treated wastewater from the primary tanks then flows to the secondary treatment system. In the secondary stage, this is the stage where the biological which means the aerobic or the anaerobic treatment of wastewater from the primary stage begins, and it removes up to 90% of organic matter. It uses activated sludge process, which use dissolved oxygen or the DO to promote growth of biological floc that substantially removes organic matter. Bacteria containing activated sludge is continually recirculated back to the aeration tank to increase the rate of organic decomposition. Bacteria attack the dissolved and finely divided suspended solids which are not removed by primary sedimentation. The water is then taken to settling tanks where the sludge again settles, leaving the water 90 to 95% free of pollutants. And the last stage, or the tertiary stage, when the effluent from secondary treatment is unacceptable, a third level of treatment called tertiary or advanced treatment can be employed. Its purpose is to provide final treatment stage to raise the effluent quality to the desired level. When the wastewater reaches tertiary stage, it still contains suspended matter and fine particles and are removed in this stage. The water at this stage is almost free from harmful substances and chemicals, and which can be reused, recycled, or released back into the environment. This stage is also called as disinfection stage, and ultraviolet is an ideal disinfectant for wastewater since it does not alter the water quality. So that would be all about the domestic wastewater treatment. Thank you for watching.